Distance. Okie dokie. Okay, let's see. Okay, take just a minute or so, let people get in. Sorry, it's late starting. Had a very important Zoom BSing session going on that I couldn't tear myself away from. If anybody has any questions of any kind, like usual, you can hit me up right now while we kind of get situated and let people stream in. I could apologize for Canvas not assigning peer reviews to people for this last week, but I'm sure it's more a blessing than anything else. I'll take care of grading those things as soon as I can get around to it. Probably be a day or two, a lot of stuff going on at the moment. Department's doing job search right now and trying to attend all of the things for that. Let's see, 332. Okay. Why don't I go ahead and start to get rolling here? So kind of beginning a little bit with last week with the string manipulation, regular expressions and stuff, we were getting into what I would call special topics in this class, right? So the sort of necessary programming stuff in R, we kind of finished out in week 7 with sort of writing functions. Regular expressions and manipulating strings, I think, is something that should be considered sort of a core skill in programming. But honestly, there are people who potentially would never use any of that stuff. If you do nothing but work with purely quantitative numerical information, you might do very little string manipulation. It's still good to know. Today is an even more sort of niche or specialized topic in that it's very easy to go your entire career without using the stuff we're going to cover in today's lecture. But it's something that R is so well suited to and is normally very difficult or sort of completely foreign, like something that they would be totally outside of what you'd normally encounter. That I really want to get into as a special topic. So what we're going to cover today is mapping, that is sort of geographical information systems type work with data and plotting in R, stuff that you might normally do with something like ArcGIS or QGIS, but as it turns out is really easy to do in R. So what I'm going to cover in today's lecture is I'm going to begin with a little bit of a unit on doing basic mapping in ggPlot. So that is, you can just give raw coordinates, things like latitude and longitude, to ggplot like they're X and Y measures, right? And you can plot scatter plots or polygons or things like that with spatial data, just like that. It works fine. I'm also going to talk about using ggMap, which is a package to mash up maps with ggplot plots. So this will allow you to do things like put a Google Maps or OpenStreetMaps image as the background in a scatter plot, and it will automatically take care of mapping real longitude and latitude coordinates onto, say, a Google Street Map or satellite map or something like that. So you don't have to worry about things like lining up a picture or something. It just sort of takes care of it, okay? And then I'll talk a little bit about labeling things in sort of spatial data, but it's actually not specific to that. We can use labeling of points in GMRepel in non-spatial data. It's just a common application. Then we'll transition to what I would call advanced mapping. I'm going to introduce the concept of simple features geometry. Simple features is sort of Well, it's actually literally is the ISO standard for storing geospatial data. So it's the way geospatial data is stored in something like ArcGIS or QGIS, and is now a way to store data in R. And I'm going to give examples and use the Tidy Census and Tigris packages to show you how you can pull down Census Bureau data and shape files and plot things. And you'll probably be shocked at how easy it is to do it in R. Okay, this sort of thing can really save you a lot of effort in your workflow. If you ever work with census data, ACS data, if you've ever had to go and download that stuff from the census website, it sucks, okay? You should not have to do that. Instead, you can use APIs and packages in R to pull that stuff down with a nice framework and never have to go and manually download things. So it turns out you can do that for most common public data sources. Okay, so let's get moving. So I want to give a quick plug. If you are interested in mapping, but specifically and especially geospatial statistical analysis in R, this is sort of the book to go to and to pick up. This is Applied Spatial Data Analysis with R by Baivan, Pabesma, and Gomez Rubio. So these authors are also the authors of the main packages in R for doing geospatial manipulation and geostatistics. They know what they're talking about, and they really wrote both the book and the packages. This is a terrific book, sort of a one-stop shop for geostatistical analysis using R. They are also partially the authors at rspatial.org, which is sort of a online big repository, textbook length treatments of doing geospatial work in R, but more up to date than Applied Spatial Data Analysis with R. Doesn't quite cover everything. Another thing you might consider taking is John Wakefield's CSSS508. I think that's still the same number it's using, which is Statistical Methods for Spatial Data. It's a hard class. Don't take this as your first class after your like graduate sequence. You want to take some classes in like MLE, preferably also Bayesian stats before taking it, but it does kind of cover the core stuff in geospatial geostatistics. Okay. Another thing you might consider are looking at like CSDE does workshops with QGIS and ArcGIS. To sort of learn those platforms too. And sometimes they're really nice for doing some operations. I don't use anything except R to do my geo analysis. Most people use something else too. You can connect them to R in various ways. QGIS can interface with R, but I can do everything I need to do in R. For very advanced stuff, there's sometimes good reasons to go to another platform. I recommend QGIS because it's open source software and proprietary software is evil. So maybe you should use that. There's workshops from CSDE on it. Okay. So let's get into basic mapping here. So back in week 5, we looked at different types of crime incidents reported to the Seattle Police Department in a single day. What I'm going to do here is use those data we covered in week 5 and just sort of map them onto Seattle to see where things occurred as sort of an example. Okay. I work with police data a lot in my actual work. So to me, this is like kind of a close example. Not these data though. These are publicly shareable. Thanks, Tiago. So X and Y as coordinates. Coordinates such as longitude and latitude can be provided in the AES argument of a ggplot and just plotted like anything else, right? So if you have spatial data, but you don't actually want to reference it to any background layer or something like that, you just want to plot the relation of things, you can just throw them as X and Y coordinates in on a plot, right? I can say, make a ggplot of my SPD data I loaded in the last slide. Just say my AES, X is longitude, Y is latitude, throw a scatter plot on. One thing you'll probably want to do, this is actually not perfect for spatial data because longitude and latitude are in degrees, and degrees are not evenly spaced. Depending on where you are on the planet, 1 degree is a different amount of distance, right? But anyway, coord fixed makes it so there's an even spacing on the X and the Y axis, right? Which is kind of nice often. If you're using something like feet, meters in your spatial units, I would use coord fixed. It gets a little weird if you get particularly far north and south with latitude and longitude though. Throw a title on there, throw a classic theme on there. It's called classic because it's ugly. So we'll get some kind of a scatter plot like this, right? So if you know what Seattle looks like, you can see that the crimes basically vaguely draw out the shape of Seattle. Most things that are reported to the police are occurring down here in sort of the downtown area and the port area. This is Puget Sound right here, right? Got kind of like West Seattle over here, Ballard area up here. The university is over here, which is usually going to have a gap because it's responded to by a different police department. Okay, so this draws out Seattle, but this is probably not what we actually want if we want to plot like police incidents on the city. We probably actually want to be able to see where they are in the city. To do that, we might use something like the ggMap package, which is probably the easiest way to do it. It's not super powerful, but it's very easy to use. So ggMap is a package that works with ggPlot to plot your spatial data directly on map images that it will download for you from Google Maps, OpenStreetMaps, Stamen Maps, and he's continually sort of adding and removing other options depending on what's sort of available to use. Okay? So what this package does is it's going to, when you make a request of it, it's going to go query an online server to get a map. This is actually using the getMap function I'm going to talk about. What it's going to do is based on the data on your plot, it's going to figure out the location on the planet that you need a map of and the scale, that is the zoom level you want, depending on sort of how much area your data take up. It figures this out for you, so you don't have to go and say, well, I want this bounding box, this square at this exact location on the planet. It figures this out for you. Then what it does is it's going to plot a raster image that is a bitmap image, like a ping or a JPEG, basically, as a ggplot object as the background of your plot. And then you can add other ggplot layers on top of it. These are points, density plots, text annotations, lines, whatever you want, right? And then it also brings to the table extra functions for interacting with the Google Maps API, which can allow you to do things like geocode addresses. So in my opinion, it's not the best way to do geocoding, but you can also do things like get the distances between places by car, by bike, by foot, or the time it would take to get from one point to another by car, by bicycle, by foot, by bus. These are kind of useful things you might want to calculate doing different types of research, right? Okay, there's other packages also to get at these things more specifically, but ggMap can kind of do them all. One annoying thing is that Google in their API made it so you cannot make requests to Google Maps without having a API key with them, which requires you to open an account with a credit card on it. So they don't charge it unless you make a large number of requests, but they do require you to have it on file. So I recommend, if you don't want to go and give them some information, use OpenStreetMap. OpenStreetMap is excellent. I'll use some Google examples because I already gave them my information. I might as well abuse their service and pull down stuff from it constantly. Okay. So when you install ggMap, you can install it by doing install.packages ggMap, but this is a common thing with many packages that interface with sort of commercial products. The web interface for something like Google Maps changes all the time as Google updates their services. And it's annoying and difficult to update an R package on CRAN. That is the process the developer has to go through to update the package. This means sometimes there will be a lag between what package is up to date on CRAN and what the up-to-date package is on their like GitHub. With something like ggMap, I actually recommend you download the version off of GitHub. If you've installed Tidyverse, you have a package on your computer called Remotes that allows you to download packages from GitHub and install them directly. This code will do that. Basically, this would automatically install the Remotes package if you don't have it. If you do have it, it won't do anything. And then this would install the package. This basically says, I'm going to use the Remotes package. In the Remotes package, I want to run the install GitHub function. I'm going to go and download a package from this guy's GitHub, basically. The package is ggMap. I forget what the tidy up reference over here does. Okay. What this is going to do is it's going to go and download and install a package from GitHub instead of CRAN. This is how you get up-to-date stuff. Okay. The problem with this is it might require compilation. If you download it and it says that it errors out, you may have to go download a compiler. To do that, there's instructions on the course website. If you have problems with it, let me know. Okay, so I load up ggMap here, and let's play with it. Okay, so one of the core functions in ggplot is the QmPlot function. What this does is it will automatically figure out a region or an area to draw a map from based on the data you feed it. So this is how easy it is. I say, I'd like to QmPlot. The data I want to plot are my SPD raw data. My x-axis is longitude, my y is latitude. Then I just added some colors to make it look nice. It figures out where on the planet the longitude and latitude describe, and then goes and grabs a Google Maps background image like this and plots my data on it. We know it did it correctly because you can see the dots all line up with the land, and there's relatively few dots in the water for SPD calls. They do occasionally respond to stuff in the water, particularly in Lake Union, but in this particular day, there don't appear to be any, okay? So this is trivial, right? If you want to make if you have some spatial data and you want to plot it on a real map like this, it's that easy. You could basically do it with one line of code if you don't want to update the colors, okay? Very easy to do. So here's a question. Does QmPlot specify Google Maps, and how do you specify OpenStreet? I think I've got this on either on like the next slide or the slide after, but basically one more argument that says source. I'm not sure if it defaults to Google Map or OpenStreetMap right now, but here I'm not specifying anything, and this looks like a Google Map to me, but I'm not positive. This may actually be an OpenStreetMap background. I forget what they look like currently. Google Maps just updated its default output for maps to make them display a little bit more stuff. So this actually could be a Google Map. You could actually check if you go and do Google Maps and zoom to this level, it's exactly the same image if it's a Google Street Map, because literally what the API is doing is it's querying out to Google Maps and grabbing the same image displayed in your browser. It's actually the same call your browser makes, so it should be the same picture if it's Google Maps. Okay. One tricky little thing in the QmPlot function to do is if you want to set a fixed color or something else for every point or whatever on your data, you need to put an I in front of it because it's expecting a variable. The I function here says this thing is not a variable name, it's a fixed thing for every point. It's obscure why it's I, and I don't want to get into it. Just know you got to do that. If you give it the text here, it's going to think it's a variable. It's kind of a dumb thing, but that's how QmPlot works. Okay. So the underlying function that makes QmPlot work, and also the QMap function, the QMap function does the same thing as QmPlot, but you don't give it any data. It just displays a map. These are all both wrappers for another function called getMap. So when you send an argument to them, they're really running the getMap function. And getMap takes a lot of optional arguments. They take things like the location. If you're using Google Street Map or OpenStreetMap, you can give it a search query for a location. So instead of giving it a longitude and latitude, you just can say like Mary Gates Hall, Washington, and it will go and make a Google search for that thing and display the map that would be produced by Google Maps when you search for it. This is kind of nice if you don't know longitudes and latitudes, but you want something. You can provide a zoom level. Zoom levels would be 3 is about continent level, 21 would be the interior of a building. If you search at Mary Gates Hall, actually, I don't know if Mary Gates does, but Allen Library in Google Maps has the full building interior, so you could query it and look inside the building if you want, right? Source here is how you would specify what type of map you want. Google will give you a Google map, OSM gives you OpenStreetMaps, Stamen gives you these sort of aesthetically pleasing maps from Stamen Maps. You can go online and like Google Stamen Maps and you'll see what they are, okay? So there's often other sources added and removed to the ggMap package periodically, but these three have been pretty stable the entire time I've been using it. Within each one of these sources, you can specify other different types of map. So for instance, Google Map offers you the option of doing terrain maps, terrain background maps, satellite maps, road maps, hybrid maps. So you can mess with all these different ones and you'll get different maps when you query it. Sometimes it's nice to use a satellite map. I like moving satellite maps sometimes for like crime stuff, I'll usually do like a road map so people have references for that kind of thing. Do what you want. Stamen maps do sort of artistic ones like watercolor maps. Toner and toner background almost look kind of like architectural or something, like they look like drawn plans, and they can be kind of nice in articles when you're going to do black and white stuff. Toner light is a nice one that uses less ink. You can also specify if you want color or black and white images, which is important for Google Maps if you're going to put it in some kind of like publication. Request the black and white one. If you publish an article in a journal, because journals still live in the 1970s or 80s, if you give them a color image, they will convert it to black and white using the crudest possible form, as if somebody was using them to do a screen print or a rubber stamp and butcher all of your images. Just give them black and white to begin with, or they will destroy something beautiful. Okay. Yeah. So you can add things on top of ggMap or ggMap generated plots like you would any other ggplot, right? So here what I've done is I've called QmPlot to make my map, but I've actually specified that I don't want a geometry. So instead of plotting the points I had in the previous plot, geom_blank says don't do any plotting in QmPlot at all. This is otherwise exactly the same thing pretty much, except I hid map type toner light here. This is not a toner light map, so for whatever reason it grabbed the wrong map type. Why I said troubleshoot my slides instead of spending all my time talking to Tiago in a Zoom before I get here. Anyway, so I then add to this a couple things. The first thing I do is do stat density 2D. Stat density 2D is a two-dimensional density plot. Have you ever seen a density plot where it draws like a nice arc around like dots you have on a two-dimensional plane? If you're doing like drawing a distribution or something, stat density 2D does the exact same thing, but across two dimensions at the same time. And so it will tend to form things like this. The highest density is here in the middle where the orange is brightest, and then these are low density regions. Everything else out here is low enough density that it doesn't even draw like a polygon around it. Okay. For this, I say AES, the fill. The fill is the color inside the polygons it draws, is equal to a stat level. This is something I haven't shown earlier in class. When you do ggplots, with some geometries like stat density, you can have them plot a calculated statistic. This here says I want it to calculate a statistic, the level statistic on the data being fed to it. I would look at something like the ggplot cookbook to know how to use these. They can be a little bit complicated. I want the geometry to be a polygon. I want it to be mostly transparent. I don't want any color. And then I add to it a gradient fill, basically saying that high density things should be red, low density things should be white. That's about it. What we end up with is a plot over here showing like the high incident concentrations in downtown and other sort of clusters of activity, right? And these are sort of where you would expect to see clusters of incidents on like crime data in Seattle, because they are combinations of both places where there are more actual crimes committed and also more people reporting them. So you got downtown clusters, but you also got like Ballard, this corridor over here and up here on Aurora. Okay. Okay. So what is color? Are you saying what is color Turas NA? Are you saying this one? Color NA here is basically, so normally by default, stat density 2D would draw a contour diagram that draws lines around its polygons. The color equals NA here is removing the lines around the polygons, I believe.
Okay, thank you.
Could toy with it and add something in there, like just do color equals black and see what happens. You might get something different. Okay. So next little thing I want to talk about for doing basic mapping before I get to SF is labeling points. So something I might want to do is label specific sort of police incidents in my data. So to do this, what I'm going to do is I'm going to narrow my data down first to a smaller area. So I'm going to say what I want to do is I want to look at only incidents reported in downtown. I'm going to get down there into downtown. I say take my SPD raw data, and then I'm just going to filter my latitude and longitude data here to get things that I know are in downtown. I did this by basically going to Google Maps, zooming in on downtown and finding the corners of the map latitude and longitude wise that sort of depict downtown to me. This is a crude way to do it, but it's probably the easiest way to do it if you don't want to go through the trouble of querying some other service or something. This is me just saying filter down to the downtown stuff. Then what I'm going to do is I'm going to make a data frame of just the assaults and robberies in the data. So I say take my downtown data, filter down to things that are assaults or robberies, and then I'm going to create a label, which is just the description of these particular incidents. Okay. See what this looks like. So what I do here is I say, let's take my same QmPlot as before, basically the same settings down here. I changed the color of my dots to fire brick red arbitrarily. I still kept them kind of transparent. The thing I've added over the previous plot here is I've said GMLabel, the data is my assaults data. Okay, now notice that this is the downtown data, this is assaults. I'm only labeling the assaults and the robberies, but I'm actually showing all the crime incidents. This is to illustrate again that you can do this sort of plot one data set here and a different data set here. As long as they share sort of like a longitude and a latitude, you can layer as many different data sets as you want on top of a single plot. Okay, I say my data is assaults, AES label equals assault label. Because of the way ggplot works, I don't have to give it an X or a Y aesthetic because this GMLabel is going to inherit the aesthetics from the QmPlot layer and know that it needs to get the longitude and latitude for X and Y. But the thing I add is I say, I want it to draw labels like this based on my assault label variable. Okay, I've used size equals 2 to draw them at a certain size. What I see over here on my actual map is it is now labeling a strong arm robbery, some other type of assault, armed robbery, you name it, at the exact points they occurred in my data. So GMLabel here basically just adds some labels to the dots. One problem with this, actually there's two problems here, is there's actually more assaults than are shown on this map, but the labels are overlapping each other. If there's a whole bunch here, these labels sit on top of each other and I can't see what's going on. Another sort of problem is that these labels are directly on top of the incident. You may actually not want them directly on top, but rather away so you can see the exact dot location. Okay, right? So the dot is probably dead center here, but the label's actually completely occluding the space, so I can't even see where the dot is. These are both sort of annoying things. You might want to offset your labels, but more importantly, you may actually want to make your labels here spread out so you can see all of them simultaneously. So to do that, I'm going to use the ggRepel package. The ggRepel package is a little helper add-on package for ggplot, and all it does is make labels able to repel one another. So basically, if labels are going to overlap, they sort of push each other away in sort of a reverse gravity model. I tried to program code to do this many years ago. It turns out it's a non-trivial problem to get labels to repel each other in a nice way. And then after many weeks spent trying to make it work, I discovered there was a package that already did it for me, meaning I wasted all of that effort. This happens a lot. Make sure to Google for things before you start writing code to do it. Someone else has probably done it better already. Anyway, in the ggRepel package, I just load up ggRepel. I keep basically the exact same code, but instead of doing GMLabel, I say GMLabel repel. Just by adding that sort of underscore repel, it's going to take care of making these labels push apart for us. This is otherwise basically the exact same code, except I did one thing to illustrate something you can do. I said here, I want fill equals black, color equals white. This makes labels that have a black background and white text. And ggRepel adds another argument to label, segment color. When your labels get pushed away from the dot, segment color allows you to say, please draw a black line going from the label to the point it represents. Okay? Black shows up nicely on these plots. So you can see, for instance, this dot in here is an assault with a firearm involved, a gun assault. This is an armed robbery over here. For ones that aren't repelled, they're just going to sit on top of where the dot is. Okay. Something you could do is you could offset all these labels, and I believe it would then just draw a line to all the ones it's offset from. Okay. So these are relatively simple things you can do. I would just say play with them until your plot looks kind of nice. Does anyone have any questions so far on the sort of ggMap or the simple plots? or labels. Quiet crowd today, that's okay. Okay, so let's go on to the hard stuff. Okay. The hard stuff, but also the fun and powerful stuff. ggMap is nice for doing like quick things and plotting some data on top of it. The real power in geospatial stuff all comes from the SF and also the SP packages. Okay, so this is about how to do actual GIS work in R. Okay. The thing is if you want to do actual GIS style work in R, you unfortunately need to learn a little bit of vocabulary. So before I get into actually running the code, I'm going to walk you through the basic vocabulary of geographic information systems, which will make it a lot easier for you to Google for help and know sort of what is breaking when you're working with this stuff, because things will break. This is a pretty complicated and challenging area to work in R. Okay. What I need to talk about, I'm going to talk about simple features geometries. I'm going to talk a little bit about coordinate reference systems, and then I'm just going to talk about what shape files are. The term shape file is lying to you. It's always more than one file, but that's what they call them. Okay. So up until quite recently, I guess the last 2 or 3 years, the main way people would work with geospatial data in R was through the SP package, which just means the spatial package in R. The SP package is super well developed. It can do just about all spatial stuff you want. The disadvantage of it is SP stores data in a really strange way that is not the way data is stored in other GIS platforms. So the way this spatial package stores data is with any polygon, every vertex of the polygon, that is every corner of a polygon, is stored as a row in the data. Now, if you can think about what, say, the border of Washington State looks like, if you imagine you have Washington State at a reasonably good resolution, which has natural borders like Puget Sound, can you imagine how many vertices are necessary to draw that polygon? There are a lot. That means a lot of rows in your data. This is not a good way to store complex things because you end up with data frames with millions of rows. Okay? This gets big, this gets bulky. Now, in the SF package, it stores an entire polygon, no matter how complex, as a single row in your data using a complex object type. The entire state of Washington's border could be a single cell in your table. This is the way these things would actually be stored in like ArcGIS or something like that. You could break it up into more by dividing it up, but each individual unit is one cell. Okay. This ends up being very powerful for working with tidy data, because normally you have one unit as one row in your data, like one observation of a state, a city. You don't want that thing broken up over multiple rows. Okay. So the more recent SF package, that stands for Simple Features, implements the Simple Features data standard in R. Okay. The nice thing with SF is that it's much more modern than SP, and as a result, they have integrated it with the tidyverse. So for instance, ggPlot has a geometry specifically for displaying SF data objects. You just use a single geom and no matter what type of geospatial object you have, dots, polygons, lines, you name it, they're all drawn with geom. As we'll see in a little bit, it makes it really easy to plot geospatial objects. Okay. SP, you have to do weird stuff. You have to like fortify data frames and then plot them like they're normal points on a plot, which gets really messy, really difficult quite quickly. SF makes it all quite trivial. Okay, so the SF package is going to completely replace SP eventually, but there's still some things that can only be done in SP. Basically, the authors of SF are the same ones as SP, and they just sort of have moved on to this new framework. Over time, SF will eventually fully replace SP. Because of this, I'm not going to talk any more about SP, but just know if you get seriously into geospatial stuff, you may occasionally have to go and use SP for something, but every day it's less and less things you got to use it for. I haven't actually had to directly work with SP in months, and I do spatial stuff for almost all my projects. Okay. So with SF, just do library SF, load it up, and we can get moving. So what are simple features? So a simple feature is a single observation of data that has some defined geospatial location. So it's data that has a point in space, and that space can be arbitrary. It doesn't need to be on Earth. It could be in some sort of abstract space, but it has a geospatial location. Okay, so features are stored in special data frames when you use the SF package. Okay? These data frames have two properties to them. The first is they have some kind of geometry. So this property describes a location. Typically, it's a location on Earth for which you'll have a coordinate reference system, but it can also be in abstract spaces if you're using them for like plotting network data or something like that, and you want to use spatial relationships of things. They don't have to exist in a real space. These geometries typically have two dimensions, like an X, a Y, like a latitude and longitude, but SF can support up to 4 dimensions. So they could also do Z, like heights, and they can also do time. So 4 dimensions is usually sufficient to do just about anything. If you want to move beyond 4 dimensions, I recommend storing things in specialty arrays. But I don't know anybody who's done any geometric work in 5 dimensions, aside from people working in certain very specific multidimensional statistical problems. It's very common in regression frameworks to use much higher dimensions, 50 dimensions or something like that, but not usually in pure spatial data work. Okay, so the geometry's property will be stored in a single reserved column in the data set. It's typically called the geom column or geometry column. It is a list column, a type of data I do not cover in this class. Basically, it looks like any other column in your data, but a single cell in there is going to look real weird. You're actually going to have, even though there's one row of data and it's one column, that cell may contain hundreds or thousands of points of information in a single cell. Because of that, you're never going to work with it directly. You don't want to crack open that cell and mess with it. It's too complicated. You're going to use other things to manipulate and deal with it. Just know there's a lot of complex stuff being there, but here be dragons. You're not going to be manipulating it directly, okay? Another thing is this geometry column will contain its own defined coordinate reference system as a property of the column. A coordinate reference system is something I'm going to get into in a minute, but basically it just tells R, or tells anything you're working with, what these coordinates are in reference to. Okay. Yeah. The other properties of it are attributes. The attributes of a simple feature are the characteristics of the location described by the geometry. These are things like the population, if your units are a state or a city or something. Okay, so the attributes are every non-spatial measure of the data frame. These are all the other columns in your data, right? If you have something like, let's say you've got geospatial data on individuals, so you have where they are in space at a given time, their location is the geometry. Everything about those people are the attributes, right? Okay, everything that's not their location are attributes, and they look like every other column. So in an SF data frame, every column except the geometry is just like everything else you've ever used in this class. The only one that does special weird stuff is the geometry column. So just don't mess with it. Leave it alone. Let it do its magic. Okay. So coordinate reference systems. Coordinate reference systems specify what location on Earth your coordinates are relative to. That is, on a Cartesian plane, where is 0, 0? So if you think about it, we're pretty used to thinking about reference points on the planet being like, well, I'm this many feet away from something, or the equator is here, or there's a North Pole and a South Pole. Okay, well, we live on an oblate spheroid, right? All locations are arbitrary. Everything that we pick is in reference to something else. A choice must always be made about what the reference is. The coordinate reference system represents the choice made in representing where those coordinates start. Okay, so that said, almost everybody uses the same standard, at least at some point, for designating this. The most commonly used coordinate reference system is what is referred to as WGS84, which I think is just World Geographic Survey or something like that, 84. This is the standard used by Google Earth, the Department of Defense. It's what GPS satellites send their coordinates around in. Okay, WGS84 is in latitude and longitude. Its 0, 0 point is the intersection of the prime meridian and the equator. Okay. Pretty simple. So if you want to define a CRS in SF, there's two common ways to do it. The most common way people tend to use is something called an EPSG code. And there's links here if you want to know more about these things. These are just numeric codes which refer to some CRS somebody else has defined somewhere, okay? If you want WGS84, it's 4326. If you want Northern Plain, Washington State in feet, it's 3689. And I know that because that's how the police data come into me, okay? Every piece of spatial data you will ever receive has some EPSG code identifying its CRS. If you are lucky and it's not coming from a garbage source, they will provide you with the EPSG code or have it encoded in the data. Sometimes, though, you'll be working with administrative data where they hand it to you and you're just going to get like geographic data and it's a bunch of numbers that don't make any sense. And then you get to go try and hunt down a CRS for it. If that's a situation you find yourself in the future, shoot me an email. I'm surprisingly good at determining the CRS by looking at the raw numbers, which is a skill you do not want to develop. It's a traumatic thing to get, but I can do it and help you with it. Okay. So another way you can define a CRS is to actually encode all the definitions that sort of define the CRS in text. This is something typically called a proj4 string. There's, I think proj5 is probably coming out eventually, but proj4 strings. These are text strings that give parameters that actually define what the CRS means. So for example, the NAD83 NSRS 2007 Washington North data that I've commonly used for some projects is defined like this. Basically, it will tell you a projection, the latitude and longitude that define the 0, 0 on its Cartesian plane, and then it tells you what ellipse the data are projected by, how to convert it to WGS84, things like that. It'll tell you the units it in. For instance, this one is in meters. Okay. All the information is there. You won't like write one of these out manually, but if you receive a geospatial data file and then you also get a text file that looks like this, be thankful. You can directly input this proj4 string and convert your data to something else. If you don't have one of these, figuring out how to convert spatial data to something useful like latitude and longitude is really hard. Okay. So these are all different ways of saying spatial data bring all their own complications. You got to learn some vocabulary. They can be a huge pain. Okay. One last thing to talk about. So geospatial data that you receive will typically be stored in something called a shapefile. A shapefile is a type of data storage that stores the geometric data as vectors with their associated attributes. Shapefiles are a name that lie to you, kind of like how I always tell you data frames are pretending to be a matrix and lying to you and they're really a list. Shapefiles lie to you about being a single file. They are usually many, many files in a zip file or something like that. You'll sometimes be emailed a bunch of them at once if you work with spatial data. There's usually at least 3 files in a shapefile. There's a .shp file, which are the actual geometries. That's like the shapes of polygons. There's a shape positional index, which is sort of an index saying how they're all related. This is just basically IDs and things. And then there'll probably be a .dbf file. This would contain all those non-spatial columns in the data set. So if you get a spatial data frame that's like a bunch of polygons with attached populations, like for instance, census tracts, this SHP contains the census tract boundaries. This thing tells them how they're all linked together, and the DBF contains their populations. Okay. If you are fortunate, there will also be a .prj file. This is a projection which defines the coordinate reference system. In my life, about 90% of the time, this file is not included, and instead I go through the trauma of figuring out what coordinate reference system the .shp is in. So it goes. If you work with administrative data, they'll never give you the things that you want, but you satisfice and figure out how to deal with it. Okay. So the DBF file, by the way, is probably just a raw text file. If you get a spatial data file and you just want the sort of data out of it and you don't want its other stuff, you can probably open this as a delimited file. You'll probably be able to find it. Other times it'll be like a database 4 file, which is a really common ancient data storage format. Okay, so that's just terminology. Now we're going to do fun stuff. We're going to make pretty pictures. We're going to work with interesting data. That terminology is important. but you can refer back to it. You don't have to memorize that stuff. You've got a resource here. Okay. So let's actually use this SF package to do things. Anybody have any questions before I move on? Anything about terminology or random stuff? That's the boring part of the lecture. Okay. Okay. Let's use this package. So the SF package has a lot of functions. It is an enormous package. If you try and browse it and look for things you want to use, it's going to be probably very daunting. There's so many different functions in it. So I just sort of label some useful things that people generally tend to want to be able to do with it. So SF contains functions to read and write shape files and other spatial data formats, stread and swrite. Stread is really smart. You can usually give it a spatial data file and it can figure out what it is and load it in. This is kind of nice. You don't have to go and track down what format it is. It generally works. GMSF is a ggplot layer that will plot any type of simple features geometry objects. You don't have to go and memorize a whole bunch of geometries. There is one geometry for working with spatial data. It's GMSF. It does everything. STSF will let you convert a data frame into an SF object, maybe providing coordinates to put into the geometry column. stjoin lets you join data by spatial relationships. So you know how we use left join, right join, inner join to join two data frames with a common identifier? If your common identifier in data frames is like latitude and longitude or some other type of coordinate, stjoin will let you join it. Maybe you have something like locations of a whole bunch of addresses or respondents in particular spots, and you want to link it onto data from a census tract. You would take the individuals, convert it to an ST data frame, an SF object, right? And then say stjoin to a spatial data frame of census data. And what it's going to do is you're going to end up with each respondent ID in your data is then going to have attached to it their relevant column observations from the census data. So you can just do nice like a left join. This is really powerful. The thing that's great about spatial joins is that it's really common to get data sources that have a spatial identifier, but no other common identifier. You might get people and an address. You might get like information on a neighborhood. You don't have any other links. It's not like there's names between these things, but if you have a spatial identifier, you can link data. There is almost no other sort of beautiful universal way to link data sets than spatial relationships. If you get good at identifying when you can take some data and link it to another spatial like data set and do these sorts of joins, you can answer a lot of research questions that are just easy and up for grabs. There's sort of like an entire industry of people out there who basically just know how to do spatial joins and can do lots and lots of cool papers because they're like, well, this is data people work with all the time. I can lump it into some geographic data, and their whole career is doing that. I'm growing to be that sort of person because there's a lot of low-hanging fruit questions if you know how to join complex spatial data. Okay. ST transform is for converting CRSs. So maybe you will need your data in a different coordinate system because they need to be in the same CRS to join them. You'll convert stuff a lot. Sometimes you need to take an SF data frame and make it no longer an SF data frame. ST drop geometry just gets rid of that column. Then there's some other things like ST relate, which I'm actually not going to get into. ST interpolate for areal weighted interpolation. I'm not going to cover this in the lecture either. But if you're interested in how to use these things, Google them or ask me about it and I'll give you an introduction. These are sort of complex things. Like if you want to create neighborhood weights matrices for spatial statistics, ST relate is the way to do it. ST interpolate and interpolation functions are like, perhaps you have a polygon, like polygons for like census tracts and polygons for election precincts. These things don't share borders. If you need to figure out how to link data between them, you need to do areal weighted interpolation to make them share a single unit. It's a complex statistical problem. Turns out it's really easy to do using SF data. I do it in most of my projects. Okay. So What we're going to work on for a minute anyway in this lecture is the voting data from homework 5. So the voting data, if you remember back to traumatic homework 5, when I gave you a terrible administrative data set and made you deal with it, that was voting data for the 2016 election in every precinct in King County, 2,600 of them. So here's a great question. Could you explain polygon in this context a bit? Yeah, a polygon is any object defined by a boundary. So a square is a polygon. The border of Washington state makes it a polygon. Anything that has a defined area that has occupies a space. So it can be just about anything you can think of. So if something has a boundary around it, it's a polygon. Things that are not polygons are like lines. A line is just a point from one spot to another. It only has or technically really only has one dimension, a length. Polygons have 2 dimensions. They have an area. Anything with an area is a polygon. Okay. And basically any administrative boundary, anything like that's going to be a polygon. Lines and points are like an exact location. They don't define any area. Okay. Anyway, so that voting data defines precincts. So we didn't use them spatially, but precincts, of course, are a spatial unit. They are an area people live in King County. You can get the shape file of King County voting precincts from their open data portal. So I downloaded this file and I provide it. You could download it if you grabbed my class. You could download my class as a zip file. You could pull this out. You could also go and grab it off the GIS portal. Yeah, I actually should have, instead of doing st-read directly from the directory, I should have provided you with a URL so you could follow along. My bad. So what I'm going to do here is say, I'm going to create a precinct shape. Doing that, I'm going to read in a shape file. To read in a shape file in R, you provide a path to the .shp part of the shape file, and it uses that in every other file and directory to construct the spatial data. Here, you used to have to be able to do strings as factors equals false, but I forgot to edit that. I haven't updated this slide, it looks like, in a year. I read it in, and then I say, I only care about 2 columns. I care about the name of the election precinct. If you remember, the SEA space some large number are all your Seattle precincts. And then I care about the geometry column. Anytime you read in a spatial file in R using SF, you're going to get this big thing that gets spit out. It's going to look at first like an error message. It is not an error message, and in fact is an informative readout telling you what that spatial data file looks like. In this case, it said it's reading in a layer from the data. This is a simple feature collection with 2,592 features and 5 fields. This means there are 2,592 election precincts. The features are the rows of the data. There are 5 fields. There are 5 columns in the data. Okay, so this is a 2,592 by 5 data frame. I filtered it down to just 2 of those columns. It says the geometry type is multi-polygon. Multi-polygon means each feature can contain 1 or more polygons. You might read something in and it might say points. That's dots on a map. It might say lines if they describe lines. This is coming in as polygons. Okay. The dimensions are x, y. It only has an x and a y. It doesn't have heights or time. And then it says this, B box. The B box is the bounding box. This defines the minimum and maximum extent in the X and Y direction of these data. So the minimum is this number. In X, the maximum is this. You're like, well, what are these numbers? It says the data come in as a projected coordinate reference system. Because this file had that .prj file, it knows to read it in as a NAD 83 Harn, Washington North, foot US data file. Well, this means that this CRS is looking at the northern half of Washington state, and these units, 120 or 1,220,000, whatever, this says the bounding box extends to 1.2 million feet away from the center of this particular CRS. Okay? The CRS center for this is probably like the middle of the northern half of the state of Washington. Its X minimum then is probably out into the ocean, basically out into the ocean slightly, wherever King County extends. So you can theoretically get useful information from this. That's what's read in when you do it. Okay. So your question, the CRS is the 0, 0 for these coordinates. The CRS is defining the 0, 0 location. It's also defining whether or not these data refer to a spherical or flat sort of data source, things like that. It defines the spheroid that it's projected onto. CRSs are kind of complicated. They tell it not just the sort of coordinate locations, but also how to translate those back onto a spherical sort of planet, if that makes sense. Geospatial stuff is really annoying because it's always implicitly three-dimensional, but we use two-dimensional representation. So you got to tell the computer how to move back and forth between three and two-dimensional things. Okay. Yeah, if you're following along, you can download this as a zip of the shape file right here. Okay. Okay, so this here, I'm just going to show you this slide and not walk through it, but this is basically the entirety of your homework 5 as a single pipe chain. So right here, what I'm doing is I'm taking that original King County elections data from your homework, and I'm just going to process it all the way down to the percentage Democrat votes in the election, percent Republican, the voter turnout, and then I join this here with a left join onto the precinct shape file. Now you might be thinking back, didn't he say something about an ST join spatial join function? If you have spatial data, but you're joining something onto it using non-spatial data, like the precinct IDs, it's not a spatial join. A spatial join is just when you're taking one geographic unit and linking it to another geographic unit. That's a spatial join. This is not a spatial join. This is just saying I'm going to use the precinct IDs to join it onto a shapefile. Okay. You could steal this and replicate it exactly if you want. I'm not going to walk through it because none of the code in here is new to you. It's just your homework assignment done quickly. What's important about this is the result. If I glimpse the result of this, my precinct votes SF, what I've done here is I've reduced it down to only the observations in Seattle. There are 960 voting precincts in the city of Seattle. There's a lot of them, okay? So it says rows 960. There are 5 columns of data. My data are grouped here because I forgot to ungroup it. What do we have as data? We have a precinct, which should look familiar to you from homework 5. We have things like Seattle precinct 11, 1256, 1550, 1552. So you see here immediately, I have exactly one row observation per precinct. Okay? I don't have multiple observations per precinct. I have a nice tidy data format. My columns are the percent Democratic vote, which is something we calculated in the homework. I also calculated sort of, it's not exactly, but basically it's inverse, which is the percent Republican vote, and the voter turnout. The weird thing we have here is this new column that you'll find in an SF data frame, a geometry. Notice here that its data type is something funky. See, this is character data double. This data type says multi-polygon US survey foot. So the data type for this column specifies that it contains polygon information and its units are in US survey feet. So 12 inches is a 1 unit in this data frame. If you look at what a single observation of this looks like, it's going to look weird, especially if you bring it out and try and display it in your console. The first observation is the text multi-polygon, a bunch of parentheses, and then lots and lots and lots of numbers. So if I pulled out a single cell, the cell that defines precinct SEA 111256, you would find that this entry is probably enough text to cover this entire slide and more. Because what this is this number is probably followed by a comma and another number, is the actual sort of in feet location of every vertex in that entire polygon. If it's a complex shape, there might be thousands of vertices. And the vertices are, again, like the corners in a polygon. Every single one of them has its own number. But no matter how many of these vertices there are on the polygon, the entire set of them is a single value in the data frame, like this number. They're all contained right there. This means you'll never look at this number directly, but just know that instead of one value here, there's many, many ones. This technically violates tidy data principles, because tidy data, so there should be one value in a cell. We're going to relax that so we don't have to expand this into like 10,000 rows of data to fully capture the polygon. Okay, so it's complicated. There's a lot there. It's a weird type of column. The cool thing about these things are they're very complicated so that it's to make it really easy for you to work with them. Let's say I want to plot the entire set of precincts, the percentage Democratic vote in Seattle. This is all I have to do. I can say ggplot my precincts votes SF data frame. I want to fill percent Democrat. So it's going to be the fill in color for my polygons is going to be percent Democrat. And then I say GMSF. You notice I don't provide an X, I don't provide a Y, I don't provide any other aesthetics. They are not necessary with GMSF. Because it is a simple features geometry object, GMSF recognizes what are the X and Y coordinates, and it figures out all the complex stuff for you. The only thing you have to worry about is maybe how you want to color them, shade them in, or draw borders around them. I say size equals NA here because I don't want to draw borders around them. In GMSF, if you plot a polygon, size is the thickness of the lines around it. I don't want any lines around it because they're really, really small polygons. I don't want to see them. I do theme void. Theme void gets rid of all the axes and everything. They're all gone. I just want a simple plot. We know where Seattle is. I don't need the boundaries to tell me the latitude and longitude and garbage like that. I just want the plot. And then I just move the legend. I wonder, I did legend position bottom. Oh, yeah, this should be legend position right. The code down here on the left is not the same code generating the plot. It's the same code in it, but this should actually say theme position right. Okay, trust me, it's the same plot. This is everything you need to do. So this is trivial, right? If you have something in the proper SF data format, it is ridiculously easy to plot geospatial data. This is the powerful thing about the SF package in R. You can draw maps to your heart's content, and you have to give it very little stuff. All the hard stuff is done for you in the background. So this thing is the full 968 election precincts in Seattle for which election results are reported. Some aren't reported if there's too few people in it, which would make people personally identifiable. This is it. It just draws the map for me. No other complexity. Any questions about that? I'm going to give a lot more examples, but it's pretty damn cool. Invalid repo specification. Remove the other slash you've got there. You got two slashes. Should be good without that slash. Yep. Okay. So what is spread counter type sum of count? Like I said before, is I didn't update some of the code in these slides. Spread is actually pivot wider now. Spread was the old way to do pivoting. Pivot wider and pivot longer are for every person on the planet, apparently, except me. Pivot wider and pivot longer make more sense. Gather and spread always made perfect sense to me. But because I teach a class, I recognize quickly when they don't make sense to other people. Pivot wider and longer make a lot more sense and are actually much more powerful functions. But back in the day, we used gather and spread. Okay. Nowadays, I like pivot wider and longer way more anyway. Okay. So we can make maps. So let's not just make maps. Let's figure out how to query and download data, including shape files using R, and then map them. This is cool stuff. What I want to talk about here is one of my favorite R packages that I use all the time. This package is Tidy Census. So Tidy Census is a package to search the American Community Survey, decennial census, and census microdata, and a couple other census-oriented data sets, and then download those data and then automatically format them as tidy data frames. So this removes about 90% of the old work in dealing with any kind of Census Bureau data, because most of the work used to be going and downloading from something like American Fact Finder, formatting it nicely and cleaning it up. Tidy Census replaces all of that with a simple query to download the data. The crazy thing is it doesn't just grab all the census data, it also pulls down the geographical boundaries of the census data you pulled down. If you ask for census tract level data, it also spits out as an SF boundary the boundary of that. So you could immediately say plot population information on census tracts or whatever anywhere in the United States, including the entire United States simultaneously with just a few lines of code. Okay. So for people who used to work with a lot of census data back in the day, this is sort of part of a lecture that will blow your mind. It used to be a giant pain to do it. You have to go grab the files manually, link the spatial data to it, clean it all up. Now it's just like a 30-second job. Okay, so this package utilizes the Census API to make requests. So kind of like that Google API I mentioned before, you got to go get an API key to do it. The thing about the Census API, though, is it is the exact opposite of the Google API. Not only do you not give it a credit card or anything, the Census API request website actually looks like the type of website that would try and steal credit card data from you. So I'm going to show you how seedy looking the government Census API website is because it amuses me to no end. This is an official government source for requesting an API key to download data. This is their website for requesting it. This is the kind of thing that you look like you'd accidentally click in an email and it would steal your credit card information, sell you Viagra, something like that, okay? You just put in an organization name and an email address and say you agree to some terms of service you're not required to read. You press the button and it gives you an API key and doesn't verify anything. So a Census API key basically doesn't mean anything. You don't have to apply for it. They just give it to you. They don't really check it. They don't really restrict it in any way. That's how it works. Okay. That is my favorite government website, by the way. Okay. So you just request it. They give you one immediately. I don't talk about APIs very much in the class. I used to have a long lecture on downloading and working with social media data, but I'm not hip and I can't keep up with that area of research, so I don't. Basically, an API, what's called an application programming interface or application program interface, is just a computer interface that exists as a native method of communication between computers or parts of computers. So when you do something like you make a query to Google Maps, so if I go like maps.google.com and I click on something, you see this address up here in the top? That is an API query your browser is doing. This up here is sort of the native language Google Maps understands. Your browser communicates it with it in this sort of language up here. Okay, that's all the API is. It's a way to communicate between different computer systems. Everything you use on your computer one way or another is using an API in some way. You don't need to know about that. It gets weird the deeper you go. Anyway, the nice thing about APIs is that if an API exists for something like the census, it simplifies access to it so that other people can go and write a package to do jobs for you that used to be hard. ggMap uses the Google Maps API, so you don't have to go and manually work with Google Maps. So if you want to pull information off of a website, it's much easier to use their API. The opposite of an API is what's referred to as scraping data. Scraping data is when something doesn't have an API or their API doesn't let you get what you want. So what you do is you go basically pretend to be a web browser or something and steal data off of what's outputted on the web browser. Okay. So like Craigslist is an example of a service that doesn't have an API because they don't want people taking their useful information they sell to people to make money. So they don't let you do it. So instead, we have people in the department who scrape Craigslist and take it because they're not allowed to use an API to do it. Sometimes you got to do stuff like that. Anyway, APIs exist for a lot of data services. Most of the time, it's easier to use an API to get data than it is to scrape it. Twitter, for instance, you want Twitter data, going through the API is a lot easier than scraping. Okay. Anyway, So Tidy Census as a package has a few useful functions in it that you would use. The first thing you do is you have to install your Census API key. Basically, you do Census API key, you put it in as a string, it will install it on your system. You have to do this before you do any Tidy Census function. You got to be able to tell it how to communicate with it. Don't give other people your Census API key or your API keys for any other service. These are things unique to you. If you give somebody your API key to a service, it allows them to pretend to be you. For the census, it doesn't matter too much. Something I've seen before is people accidentally giving out their Twitter API key. If somebody has your Twitter API key, they can send tweets through your account. Don't accidentally give people like API keys. Okay. So other things, load variables. This function, you will give it a year of the census or ACS you want and which data set you want to get variables from, and it will spit out a data frame containing a searchable list of every variable in that data set. Now, if you ever worked with the census, you know the census contains tens of thousands of variables. So this data frame might take a little while to download to your computer, but it's got everything you want in it. What you'll do is you'll use string manipulation functions like what we learned last week to search through the different columns and find the variables you want. This is sometimes easier than working with American Fact Finder if you get good at string manipulation. Next ones are get decennial and get ACS. Get decennial gets the decennial census, that is the actual full census, the every 10-year census, which is what decennial means, and get ACS, which gets the American Community Survey. Okay? Within these functions, you'll do things like specify the variables you want, the geographical unit you're working with, like states, tracts, blocks, but also things like zip codes, the year of the census or ACS, and then whether or not you want the geometry to come with it. The geometry are like the boundaries around the state, the tract, the block group, whatever. Okay. So let's put this into action. So I load up Tidy Census here. I load my Census API key, or that's what you would do if you're running this yourself. I don't have to because mine's saved on my computer. Then what I do here is I say, okay, I want to get all the variables in the 2015 5-year ACS. So these are ACS5 estimates for 2015. So I say load variables, 2015, ACS5 is the data set. So this is going to get me all the variables in the 5-year ACS that for the ending year 2015. ACS5 is the 5-year estimates. So this is estimates made on data from 2011 through 2015. If you want to learn more about the census, Google it. It's one of the best documented things out there. So I just show a very small subset of these data. So the ACS 2015 VARs thing here is probably 50,000 variables long or something like that. What you get out is something like this. So I just show the first 10 through 18th rows of the data and print them. We get things like this. Variable B01001_008 is the estimate of total males of age 20 years. The concept is sex by age. So you can see the sort of things you'd be able to search through in the ACS to get things. If you knew you wanted to search for the sex of individuals in the ACS by age groups, you could, for instance, do string detect on concept, sex and age, and get sex and age. Okay? And it would give you these sorts of variables. You might have to search through the label variable here to be like, well, I'm looking for males. I'm looking through 22 to 24, whatever. But you can search through this data set and get things. And then what you want is the variable name over here, which is what you're going to actually give to the functions to request a variable. Okay. Feel free to stop me at any point if anything I'm saying doesn't make any sense. We're going to get into examples here as we go. So now I want to download some census data. So what I want to do is I want to get census data for the entirety of King County using this ACS data. So I'm going to say I want to get ACS data. The geography I want are census tracts. Census tracts usually have about 4,000 people in them. They're a really common unit for at least sociological and demographic analyses. I say I want data for the state of Washington, King County. Geometry equals true says give it to me with those geographical boundaries around them. And I'm only going to ask for 2 variables here. I ask for B02001 underscore 001E, which is the estimate of the total population in the tract. And then this one, 2009 underscore 1E, is the estimate for the Black population in the tract. Okay. I say here, give me output wide. So there's two ways to get data out of the ACS. You can get it in long format, which is technically tidy, or wide format. I recommend you actually get the wide format. Long format will look a little bit weird to people. Wide format puts each measure in its own column. For instance, variable B02001 underscore 001E here is a column, and within it would be the population estimates for the census tracts in question. If you ask for it in long format, each measure gets its own row. If you ask for 10 measures, each census tract would get actually 20 rows, one for the estimate and one for the margin of error. This is confusing to people. I say do wide format. You get more columns, but it's easier for most people to work with. The resulting data frame looks like this. The GeoID here is a census tract identifier. This is something referred to as a FIPS code, which says 53 is the state of Washington, 033 is King County, and this is census tract 317.05. If you work with census data a lot, you recognize these things immediately. There's also text telling you that that is what it is. Then, for instance, this says there's 4,271 people in this census tract with a margin of error of 266, and there were 469 Black people estimated, but with a huge margin of error of 345 because we can't precisely estimate Black populations in Seattle because it's a super white-ass town. Okay, a lot of information here. Yeah, wide gives each census tract a row, exactly. Which you'd think of as tidy data, but it's wide because to the actual tidy data format is multiple measures per row because you've got these estimates and margins of error. Yeah, I prefer the wide format, which is what I would think of as tidy data. Okay, and you see here again, geometry is a multi-polygon, but in this case, the unit is degrees. It's in latitudes and longitudes. It's a multi-polygon. This one's at negative 122, 1336. If you know anything, negative 122 is approximately sort of like west-east our location in the planet, right? Okay. Any other questions on that? We've loaded some data in. We can do stuff with them now. So first thing I want to do with this, and this is something you'll probably want to do, I want to drop the margin of error column. I'm not too worried about the level of error. I'm going to rename these into usable variable names, and then I'm going to calculate a proportion measure based on the census any Black population. So what I say here is take my King County data. I say select minus ends with M. All of the columns that come out that end with the letter M from tidy census are margin of error columns. If you're like a demographer and you care and want to use these things, you'll want to keep them in. For me, I'm just doing examples, so I want to get rid of all those margin of error. If you're working with decennial census data, it won't have these because they're actual counts and not estimates. ACS data is estimated, it's survey data, okay? I rename my variables, so I know this variable here is the total population. This one here is the any Black, so that's people who responded to the ACS saying that they are either only Black or at least multiracial Black as one of the categories. Okay, so it's probably the widest Black population definition in the ACS. I then mutate a any Black variable, which is any Black divided by the total population, to give me a percentage any Black in census tracts in King County. So my resulting data just has a total population, an any Black, and it still has the name of the census tract, its FIPS code, and its geometry. Very simple little data set. So let's do some mapping with it. I can say, take my King County data, send it to ggPlot. I'm going to AES fill equals any Black. So this means that my polygons are going to be filled with the estimated percentage Black in every census tract in King County. GeoMSF size equals NA is going to say don't put any outlines around my polygons. I say here, coordinate SF. This is a function for ggplot to change the coordinate projections for it. I converted it or said the CRS is WGS84 here. This just altered slightly the way that my projection looked. This is totally unnecessary basically for the CRS, but it made my plot look a little less scrunched. This, however, is useful. Datum equals NA in coordinate SF will remove what are called graticule lines. These are things like the meridians and the parallel lines. Sometimes you'll get those vertical and horizontal lines that make it look like you're looking on an atlas or something. If you have a plot with those and you don't want them, do datum equals NA. I left that in just to show you how you can get rid of them if they're a problem on your plot. I then say I want a scale fill continuous. So I'm just going to alter the colors displayed on my plot for the any black variable. And I just say my low should be this and high. These are hexadecimal color codes. I actually just picked these because I wanted a nice lavender color that jives with the overall look of my slides. You do yourself on colors, okay? A minimal theme and a title, okay? If you're interested in what these things do, there's some documentation here. What's more important is what this plot looks like. So the plot looks like this. This is a plot of the proportion black in every census tract in King County. So this is King County right here, and you see the highest gets up to just over about 40%, about 0.4 proportion, kind of in southeast Seattle, and getting down into more like the Renton, I guess kind of like White Center area down over here and stuff, right? Now, if you know what the Seattle area looks like, what looks like a problem with this plot? What do you not see in here or makes it hard to tell where things are? Beautiful. There's no water here, right? If you looked at an aerial view of King County or Seattle, there's water. Yeah, there's some water here for Puget Sound, but what, for instance, major bodies of water here are missing in Seattle? What do you not see? Yeah, that lakes that disrupt your otherwise smooth commute. So for instance, you'll see, I don't know if I can zoom in on this. No, I can't. Okay. This over here is Lake Washington. It's hard to see, but there's a bunch of really funny shaped census tracts over here. You'll see there's this nice smooth line running through here. That's actually the center of the lake. And because census tracts actually extend out into the water, they just happen to meet. This shouldn't be over here if we really wanted to display what Seattle looks like proportionally, because it makes some of these census tracts look like they're gigantic because they're like 75% water. Okay, so this little demonstration is showing you kind of the power of SF here in a second. Let's get rid of all that water. So what I'm going to do is show you a simple function we can use in combination with the boundaries of water bodies in King County to delete the bodies of water from our prior plot. So I make here a function called sterase. This is a function which takes an x and a y. The x is going to be the thing that we want to delete water from, and the y is going to be the actual boundaries of the water. Okay, so we're going to delete y from x. How does this work? This function is, it takes the ST difference. ST difference subtracts one geometry from another geometry. So it's going to begin with the geometry we want to keep, the thing we want to delete stuff from. What is it going to delete from this x? It's going to delete this big statement over here. Let's work this one inside out. ST combine will take whatever is inside of it and combine it all into a single geometry. The thing is we're going to download the bodies of water, but the way the bodies of water work is every body of water, every lake, every river, every pond, you name it, is its own geometry. We want to combine them all into one big thing that we can delete all at once. So I say, let's combine them together. We then need to resolve their internal boundaries because some of them may overlap or touch each other, and we got to fix these problems. ST union fixes their internal boundaries by sort of gluing them all together. Like imagine you took all these different boundaries on top of each other and squished the stack down, and all the lines sort of meet up nicely. As a result of doing that, sometimes you get some errors in geometries. You might get holes in things that shouldn't have them, or you'll get like loops in their polygon lines. ST valid will fix those problematic things. I put this in here not because it's always necessary, but because if you ever do this in real life, frequently you're going to get weird geometric problems. STMakeValid will usually fix those problems. You'll get errors like, it'll say things like self-intersection. You'll Google Stack Overflow, and angry people will say, well, if you're working with GIS data, you should know how to deal with self-intersections. You don't want to deal with that. Instead, STMakeValid will usually fix the problem for you. Okay. So what we're really doing is we're saying we have a geometry on the X side, we're going to delete some bunch of geometries mixed together from it. How do we use this? The first thing I need some water to delete from my census tracts. I'm going to get the King County bodies of water. To do that, I'm going to use the Tigris package. If you've installed Tidy Census, you have this package. Tigris is the thing that actually generates the shape files for Tidy Census. I say here, get the Tigris files for the area of water, in Washington State, in King County, an SF class object, so a simple features. This gives me every body of water in King County in Washington. Then I say, take my King County data and then erase the water. This is the function I just generated up here. STErase will take the King County geometries and delete all the water from them, leaving us with King County with no water. So this function here I've walked you through, it is in no way necessary for you to understand how anything here works. What's important is to know if you ever want to work with census data and make the water disappear, steal this function and write me a thank you note. That's about it. Okay. So to use this, we just do the exact same plot. I deleted all the water from it. This is the same plot from before with the KC no water data instead of the water data. This is already beautiful, right? This took that census data, plots the same thing, but just deleted all that water. So now we can actually see King County from the air. And you can actually see this as a really lovely plot because it has every tiny little body of water in King County. All those mountain lakes and ponds, the big rivers, the streams, everything's represented in here. If you zoomed way in on this plot, you'd actually see there's a great deal of detail. I don't know if I can actually, can I open image in new tab? Well, let me zoom in. Yeah. So I can zoom, this is the max the browser will let me zoom in. You can actually see if you zoom in, like save this to your computer, you can zoom infinitely in on this because it's a vector graphics file and see these rivers all the way down to like the tiniest little lakes in Seattle and stuff. It's incredible stuff, right? And this will render instantaneously in R. In fact, R will draw these things much faster than ArcGIS or QGIS will. Okay, so this is beautiful, right? This is super cool. Okay, so you can do this kind of thing, and I highly recommend you do. The reason is that in the most professional terms I can say, people fucking love maps. If you do like a presentation somewhere, you write a journal article, people love maps. You go give a job talk somewhere, show them some spatial data plotted on the city you're in. Oh, you'll see everybody in the room look at it and react. They're like, oh, I know these things. It gives you this real life reference to stuff. Geospatial stuff is one of the best ways to convey relatable information to people. If you have anything with a geospatial unit, make use of that and show it because it anchors people to the real world like no number possibly can. Okay, make use of this kind of stuff. It's super useful. Okay. Anyway, and as it turns out, it's really easy by and large, especially working with like census data. Okay, here's to give another example. I'm going to do more or less the same kind of thing, but show you how you can generalize the thing I just showed you to other stuff. So my roommate, Steve, is from the greater Chicago area. He's actually from Rockford, Illinois. I'm going to use an example from the state of Illinois. This time, I'm going to do exactly what I just did, but I'm going to use a whole state instead of King County. So I say, I'm going to do an example state. I say PB state. I forget why I picked PB. I'm going to say, get my ACS data again. Still get tract level data, but give me the state of Illinois and no specific county. So I'm saying, give me every census tract in Illinois. There's thousands of census tracts in Illinois. You'd think this might be a slow thing to do. It's not. It's just as fast to do the data stuff, just as fast to do the plotting, to download everything. It's quick. Everything else is the same basic code here. It's %black. I do a plot. If you look, this is actually the exact same plot I just did for the King County data. I changed nothing. This is the state of Illinois, %black at the census tract level. There are thousands of census tracts depicted here. If I do, for instance, again, open image in new tab, zoom in, this is as far as I can get in, you can kind of see there's these little specks and stuff. This is the city of Chicago. There's like 900 census tracts in the city of Chicago, and I assure you, every single one of them has a polygon on this map. Okay? This is powerful. This is a very generalizable tool. Anything you ever want to produce or display with census data, ACS data, anything like that, at any geographical level the data are available at, you can steal this code and do it exactly, and then also link it to all the other data you have, do all your geospatial stuff, plot things beautifully, make gorgeous maps in like 5 lines of code, right? This is a really powerful thing in R that I think is sort of not advertised enough. It's a very good geospatial data platform. Okay, so let's dress this up in one more way. So maybe if I look at something like this, I'm like, oh, well, I see %black is very high in a few pockets over here around the state of Illinois. Maybe I would guess that all of these pockets are actually the urban areas, the major metro areas in Illinois. And in reality, Illinois is super white as soon as you get outside of Chicago and these other places. Let's test this hypothesis by drawing the cities on top of this map. Okay, so a neat thing about GeoMSFs and in ggPlot is like any other layer in ggPlot, you can put multiple SF geometry layers on a single plot. You can just plot them on top of each other. This is neat if you have overlapping geometries of different kinds. Things you might use this for instance, things I use this for all the time. Maybe you've got like a bunch of polygons, but you want to add points to it. Maybe you want to show the cities and states. Maybe you want to show individual crimes and police beats. Maybe you want to do things like add lines, like for instance, something I often do. I get all the census tracts in a city, but then I overlay the street grid, and then I overlay the crime data on top of it. Many different layers all the way down, okay? Other things might be adding outlines or highlights. You could add elevation contours, or what I'm about to show you is show all the urban boundaries in the state of Illinois. So here's a great question. I might have missed this. Could you say what ACS is meaning in the data? ACS is the American Community Survey. So the American Community Survey is the Census Bureau's continuous rolling survey for collecting socio-demographic data in the United States. If you want anything more detailed than what's in the short form census, you probably want it from the ACS. This is where you get all that great data on like low-level income data and things like that. That doesn't come from the census by and large. That comes from the ACS. And it's actually it's a survey, and so it's estimated data. The 5-year ACS is the most accurate because it's averaged over 5 years. Okay. Yeah. I use ACS and census data all the time because I'm kind of pretend to be a demographer sometimes. Okay. So what we're going to do here is show some urban boundaries. So what I'm going to do is I'm going to, again, use that Tigris package I mentioned before. Tigris includes things like all the urban boundaries in the United States as a shapefile. So here I want to get urbans. Urbans is going to be every urban boundary of every city in the entire United States. I just say, use the Tigris package, give me all the urban boundaries. CB true says give it a simplified boundary. If you're not working with really small geographies, CB equals true will speed up the download of these files. Might not be surprised that if you download the urban boundary of every major metro in the US, it can take a little bit of time. Class SF just says give it to me as an SF file in our nice format. The resulting data frame looks like this. You get columns saying like identifiers and FIPS codes for the urban boundaries, but then you see things like the name. The first observation is Colorado Springs, Colorado. It has its land area, its water area, and then, of course, a geometry column showing its multi-polygon geometry. So every row of data is a different city. Here's South Bend, Indiana, Colorado Springs. You know, South Bend, Indiana actually covers 2 different states, okay? Indiana and Missouri. A lot of urban boundaries are multi-state. Okay. So here what I want to do is I take my urban data and I filter it down to string detect in the name of the location, capital IL. This is going to give me all the ones that are in Illinois. This is me using a little string manipulation to filter this down to just the places that are in Illinois. They won't I use string detect here because they won't always be at the end, because I could have a city that, for instance, is in Illinois and also like, Wisconsin or something like that, right? Okay. So this is every urban boundary in the state of Illinois. Let's augment the exact same plot from before. I still take my Illinois state data. I still fill my polygons with percentage black. I still do a GMSF with no boundary, but I just do another GMSF call. So I say GMSF, but now we're going to use a different data frame. Data is my urban boundaries of Illinois. Color equals black is going to make the urban boundaries of these cities black lines. Fill equals NA means there's no fill. I want them transparent. I just want to draw a line around the cities. Size 0.1 says I want a thin line. Inherit AES equals false says don't inherit the AES from my earlier ggplot call, which is size equals NA and fill equals black. Often if you want to add a layer, but you don't want the aesthetics from the prior layers to be in it, you want to do this, inherit.AES equals false. Every other part of this plot is exactly the same as my prior Illinois plot. So this is an example of iteratively adding things to a plot you've already made. What we get is this super cool plot. This is the same percentage black in Illinois plot, but now every urban boundary of every major city in the state of Illinois is plotted on top of it as a thin black line. So you can see, for instance, the Chicago metro is this massive sprawling thing right here. And in reality, all of the concentration of Black folks living in this area are actually right within the sort of southeast area of Chicago and a little bit right here off the center. Similarly, this massive pocket of Black folks over here in the southwest of the state is another major city. And in fact, you'll see there's only a couple census tracts that have any substantial population of Black folks in the entire state of Illinois that are not in a major metro. And this sort of highlights the point of Black population in the United States being highly concentrated in urban segregated neighborhoods. Okay. So kind of a cool thing. So here's a question. Why do we need to remove the polygon fill? So we remove it here because if I didn't, all of these metro areas would be filled in with a solid color and I wouldn't be able to see the percentage black in the census tracts inside of them. So I just remove the polygon fill for these lines here. Okay. Oh, could I fill it with a different color? Yeah, I could do whatever I want. So you could do something like maybe make it partially transparent so you can still see through it and then do your fill in a fixed color. That might be a good way to do it or something like that. Do whatever you want. You got all the flexibility of normal ggplot. It takes all the same arguments and all the commands, which is the cool thing about like the GMSF. It does everything ggplot can do with all the same arguments, all the same power. It works exactly the same way. You just don't have to interact with the actual spatial data itself. It makes it really easy to do stuff. Okay. That's about all I got. So I can field questions, anything folks got. It's a pretty quick lecture. Is there only a way to show only the urban boundaries that fit within the state lines? Absolutely. The way to do that would be to use the subtraction function like that st erase I did earlier. And then just basically you would erase everything that's not in the boundary of the state of Illinois. So what I would do, the easiest way to do it here would actually be to get the boundaries of the surrounding states and subtract them all from the data frame. Yeah. Could you fill in the negative space? Yeah, you absolutely could. To do that, I would get the full boundary of the state of Illinois, and I would subtract from it the metro areas, and the resulting thing you would get would be that negative space. And the urban areas without colors, yeah, those are in other states. So for instance, this over here, this is in another entirely different state. This is in another state. This is in another state. I just left them on because I actually thought it looked kind of cool this way, because it shows how urban boundaries don't match state lines. It's entirely possible for a city to straddle multiple states. Is there a way to use a different palette for any black within the city boundaries? Oh, that's a really cool question. Let me think about that. How would you do that? Yeah, the way to do that actually is what I would do is I would probably make it so that the data inside the urban boundaries is a different data frame from outside of the urban boundaries. And I'd plot two different data frames on it, one with one color scale and one with another. Something like that. Probably other solutions too. Yeah. Love these questions. This is great stuff. Anything else? Okay, well, people are thinking. So technically speaking, you are done with my class homework-wise as of turning in the assignment for this week. If you feel like it, there's an optional homework assignment, which is worth points. But like I've said before, the points in my class, it's kind of like whose line is it anyway? The points are basically made up. You're going to pass this class unless you've turned in nothing. But there is a homework 7 template. This is a exercise using the restaurant inspection data from the string manipulation lecture to plot where things will poison you throughout the city of Seattle. This is how you can go and see that one frat that will kill anyone who walks into the kitchen. You can find it if you want in the restaurant's inspection data. You'll get bonus points if you turn it in. There's no peer review for it. I do all of that. Okay. Here's a question. Can you go back to the loading the variables? How do you know the variable name? So how do I know B02001 underscore 001E is the question. The answer is this. I went through this massive data frame and searched for the label of the thing that I want and grabbed its variable name like that. That is how you do it. They are not intuitive, but what you do is you use this data frame as a big lookup table. Now, so I normally don't have a lab on the geospatial one because usually only a few people do it, but I'm happy to meet in lab. Just shoot me an email. If literally one person tells me via email they're going to show up to lab, I will do it because my time has no value. It's actually nice and relaxing. I love hanging out in the labs and chatting with folks, so I'm perfectly fine with it. I find teaching, well, sometimes exhausting. It's also very like kind of therapeutic to interact with other human beings because, you know, I haven't seen them very often in the last like 9 months. And sadly, this counts now. Did that make sense on finding the variables? Great. Yeah, just a big lookup table. Other ways to do it are to go through like American Fact Finder or its equivalent online and get the variable names from that. Also, if you have existing census data of some kind, like you're already working with it, these are the official census variable names. So you can just take them from your existing project and use them to download. Yeah, which I've done before too. Cool beans. Now I got nothing else. So feel free to head off. We have a single lecture remaining in the class next week. It's going to be my extended rant about reproducible research and why you should be involved in it. And then I managed to get you to sit through that because at the end, I will cover how to do model results and tables and nice things like that. So subject you to a rant, show you something useful for all your other classes and stuff. Okay.
Thanks, Chuck.
Thank you, Chuck. This is a fun one.
Yeah, that was awesome. Appreciate it, man.
Absolutely. Yeah, I love this stuff.
Thank you.
Next week is similarly cool too.
Out of curiosity, have you ever worked with a guy named Peter Kuhn at the King County? He runs like a group called Kugos after work hours about GIS and mapping data. Okay.
No.
Okay.
Yeah, I'm not an expert. I consider myself with GIS stuff to be a bit of a hedge wizard, like somebody who's like taught themselves this stuff just entirely on their own. So I don't speak the same language as most people who work in like GIS stuff, and I don't know how to do fancy stuff. But it's like I mostly do a lot of spatial analysis and crime stuff. So that's the kind of thing I do. Real GIS people, for instance, actually Phil Hurwitz at CSD is a real GIS guy. And so it's like we have a bunch of people at CSD who are actual GIS people with like degrees in doing that stuff. So
I just wasn't sure, like, if you knew if there, like, how much relatability there is between GIS language and terminology versus what we've talked about today, because
Oh, a lot.
a lot. Okay.
Yeah.
So this is sort of translatable.
Yeah, the simple feature stuff is the same way that stuff is stored in the major GIS platforms.
Nice.
Yeah, Tiago asked you a question too. He said, "What's that thing called?" You were talking about.
What's what thing called?
Oh, you mentioned like a project name, like Coog
Oh,
or something?
Kugos. Hang on one second. Let me
Yeah.
give you a link right quick.
Cool, thank you.
Yeah, so they met a couple of times before the pandemic hit. I got introduced to them by my cousin, who is incidentally from Rockford, Illinois. And yeah, I was hoping to do some like public health work with, mapping in the city, because I was one of those dorks that read the map maker's book and I just like it. But I had like no handle to get my head around it. So
Yeah.
I was like, oh, maybe this will be a good entree. And then they were all talking way above my head. So I was like, crap, I have to go learn more.
I will have to ask, is your cousin in the age range of like mid-late 30s?
Yeah.
What's his name?
David Bittner.
David Bittner. Okay, I'll ask Steve.
Okay. His dad is a pastor named Denver Bittner and is apparently a super extroverted social guy. So if he knows Denver Bittner, there's a chance. Yeah.
Oh, that's great.
I would love to know if there's a connection, because, all people from the same city know each other, right?
But I mean, yeah, Rockford's reasonably big, but you never know.
Yeah, you never know. It's worth a try.
Cool.
All right, take care.
Okay, see you next week.
Bye.
Later, Chuck.
Later.
I'll probably be here next week too, man. That was awesome. And I definitely need some help with I think you said modeling and output and stuff like that.
Oh yeah, awesome. Yeah, come and shop.
All right, take it easy, bro. Be safe. Say hi to Steve and everybody else, the squad. The four of you make me so happy.
Will do.
All right, later, man.
Bye-bye.